Hello and welcome. Enrichment/discussion. We have a difficult integral. I don't know why I put 3-star there. This is actually a 5-star. I'm going to do a little bit of an analysis of that. It's got an easy start and then it will get quite tough in order to evaluate it. Okay, so it's the integral of 1 over, I've got in the bracket 2 plus x and then a square root 1 minus x squared. Lots of mistakes in the copying process. So pause the video if you want to have a go. Otherwise, wait for the solution. And if you manage this particular one, I don't remember the answer. I think it's got pi's and root 3's, I think, something like that, but I can't quite remember what we should get for this particular one. Okay, this is the solution. I did say this is actually quite easy to start because the problem quite clearly is that maybe we can try a square root substitution, like u is equal to that, in the hope that it might simplify from there, but this does not actually give us something sensible. So I'm not going to try it here. I did try, of course, when I first saw this particular one, but the sensible substitution for something like this is to get rid of this square root with a sine substitution or a cos. Sine is probably better. X is equal to the sine of theta. And in fact, the substitution is not that. The substitution is, in fact, theta is the arc sine of x. But we do write it like this because, of course, it is actually easier for our algebra. Dx is equal to the cos of theta d theta. And the limits, we go 0, we'll map. And when we go into theta into 0, and the 1, the arc sine of 1, is pi over 2. So this is what will happen once we transform this integral. So the first step is not difficult at all. Let's see what will happen. We're going to get the integral from 0 to pi over 2. 2 plus the sine of theta in this bracket. This, of course, will be 1 minus sine squared of theta. The 1 on the numerator, and my dx. Let's actually write part of the dx, the cos of theta on the top, cos of theta, and let's put the d theta at the end. I'm not gonna obviously just write more stuff from there. That's, of course, the same as that. So now we have, of course, a very standard integral. And I say standard if you are an integration expert, you're doing an awful lot of integration, or you're a further mathematician, as it turns out to be these days, because this kind of stuff has moved higher up into further maths, so you don't get to see it if you do just kind of like ordinary further maths. How do we integrate now 2 plus sine theta? There's a couple of ways that you can do this. The standard way of doing this particular, we won't need this particular one. It's got limits, so once we transform the limits, this substitution is gone. We're not going back. So let me just get rid of all of this. Is what I call the little t sub, which is basically the little t identities. Again, that's my own words. Little t identities. It's basically the tan half angle. And of course, I think sometimes it's called the Weierstrass substitutions or things like that. I personally, if I was doing this for myself, I don't use Weierstrass substitutions hardly ever, because there's better alternatives. That's how I was taught how to do things, and therefore I only do it because it's part of a syllabus. It has theoretical value, but sometimes not practical value. So the first attempt is to actually do it with the little t identities. Okay, so if you know how this works, we're going to use a standard substitution for something that has linear combinations of sines and cosines. T is equal tan of theta over 2. That's the standard substitution. This is actually a very standard integral from this line onwards, but I'm going to do this in a slightly different way to actually show you an alternative to this substitution. Okay, what happens there? We're going to differentiate that. dt by dx is, of course, a half sec squared of theta over 2. dt by dx still is equal to a half 1 plus tan squared of theta over 2. And of course, we can go back into little t's now, because of course that's my t. So that's a half bracket 1 plus t squared. And if we rearrange this particular one, actually, I did say dt by dx there is actually incorrect. I do apologize. Should be dt by d theta. I'm going very absent-minded. It's actually my 5th video that I'm filming today, so I'm exhausted. Try to get a few things done so I can have a total break over Christmas. Okay, so this is now so far so good. And I need to make, of course, d theta the subject. So d theta multiplying across, it'll give me 2 over 1 plus t squared dt. I just flipped it and rearranged it. And because I don't want all these workings up there, I'm going to write my... Actually, let's leave it there because I'm going to put it in there and then we don't need it. So that's the second stage of the substitution. The third stage of the substitution, let's change the limits. When theta is equal to 0, the t will also become 0. And when theta becomes pi over 2, tan of pi over 4 is 1. So it goes back to the original limits, essentially 0 to 1 as we had it originally. And the last thing we need to do is to get an expression for the sine of theta in terms of these little t's. This is a standard identity. If you're doing a lot of work and you're not being asked to prove, you can actually write this identity. The sine of theta is equal to 2t over 1 plus t squared. It's a well-known identity. The cos of theta will be 1 minus t squared over 1 plus t squared. But here I'm going to actually give you a way to prove this, which perhaps is not the standard way of proving this, and it's quite interesting. So if you have to prove that the sine of theta is equal to that, I'll start as follows. The sine of theta is, of course, 2 sine theta over 2 cos theta over 2. A little bit bizarre start, but then I can say I'm going to divide the sine of theta over 2 by a cos of theta over 2, but of course we don't have an equation here, we have an expression. So if I divide by a cos of theta over 2, I need to actually make this into a cos squared. Pause for a second, just check that this is exactly the same as the line above, because of course this cos theta over 2 and this cos squared will cancel, so it's exactly the same. And the reason I've done that is because I've just created there 2 lots of the tan of theta over 2, which will go back to t's. And this cos squared, which I got on the side now, I can actually write it as 1 over sec squared of theta over 2. And of course, this is an identity. Sec squared is 1 plus tan squared of exactly the same argument. So that's exactly 1 plus tan squared of theta over 2. And of course, this is just t, this is just t. And this now, if you look at what I've written up there, is the sine of theta is 2t over 1 plus t squared. So that's another way, no triangles to be drawn, just pure algebra. So I'm going to rub this off. I hope you followed it. And I'll do similar things for the cos if I had the cos to be found. So I've got all my results up here. So I'm going to transform the integral, and that is now from 0 to 1. We got a 2 there, plus, and that's on the denominator, so we have to be careful. And the sine of theta is 2t over 1 plus t squared, or 1 on the top. And my d theta, it's up there somewhere. My d theta is 2 over 1 plus t squared dt. So the whole integral has been changed into t's. So let's see what happens. It's 2 fractions multiplying each other, so 1 times 2. Let's see what will happen. Let's change pens as well in the meantime, because this one is dead. So we're having 0 to 1, and we have 2 times 1, or 2 on the top. And on the denominator, we got this bracket times in the 2, and this bracket times in this lump, which of course you will cancel that. So we're going to have, I'm just not doing it in steps, I'm just writing the answer. So that's 2 lots of that, 2 plus 2t squared. That times that, and then when I times that, it will leave me plus the 2t dt. So this looks significantly nicer. It's some kind of quadratic at the bottom. I got a factor of 2. Can I cancel it? You can, but me personally, I like it to actually, I do things in a very weird way sometimes. I'm going to actually double it. I'm going to create more 2's in there because it suits me. It's because I see completing of the squares instantly in expressions like this, such as when I have at squared plus at, or minus here, okay, if it's the same coefficient, like I got a 2 and a 2 in there, I immediately create 4's, okay, because it's an easy completing of the square. I'll just see this expansion basically, 4t squared plus 4t, and that will of course complete to a 2t plus 1, and I just adjust the numbers. If that doesn't make any sense, have a look what I'm doing. So let me just multiply top and bottom by 2 first of all. It might make sense as I'm doing it. 4t squared plus 4t there, plus 4, and of course 4 on the top. And if you look at what I was just referring to, it's just a little shortcut. It comes with experience, having done this a few times. This is going to be a 2t plus 1 there, and in order to do that, I borrowed a 1 from this 4, and I got a plus 3 dt. And of course I'm doing that because I can see whether this factorizes, first of all, and secondly, this now I can see it's an arctan of some sort, so I don't want to waste the line. So what I'm going to do, I'm going to write this straight away into a square root of 3 all squared to create a standard arctan. I'm not using another substitution. We are at enrichment level now, and we should be able to recognize this as the arctan of 2t plus 1 over root 3 with some constants to be adjusted. So let's have a look what's going to happen in there. First of all, we got that 4, which is on the numerator. So I'll pull it on the outside. It's going to be extra bits at the front, but I'm going to write it at the back. It doesn't really matter. This is the arctan of 2t plus 1, 2t plus 1 over root 3. And of course the arctan will produce 1 over this quantity here. So at the end we're going to have a 1 over root 3. But there's one more thing. If I differentiate this arctan, it produces a times 2 from the 2t plus 1. So I need another half. If you cannot quite see that one, or I'm just pushing it too hard with this, go and use another substitution. U is equal to 2t plus 1. And this will become a lot simpler. It'll be of the form, of course, u squared plus square root of 3 all squared, and then all the little constants will take care of themselves. Okay, so it's I hope you can actually see it as it is. So I just need obviously evaluation brackets because I've got this to be evaluated between what? 1, 0 and 1. So this will give me, first of all, I've got 2 over root 3, half times 4 over root 3. I'm going to pull it outside the integral. No, the integral, the bracket, sorry. And then I got the arctan of what? I'm putting 1. So that's the arctan of 3 over root 3. 3 over root 3 is root 3. So that's the arctan of root 3, which is a nice number. Minus the arctan of the other quantity. When I put 0 in there, that's the arctan of 1 over root 3, which is also a very good number. And what we'll get in there is a very simple answer, which of course it gives us 2 root 3. This is pi over 3. This is pi over 6. The difference is of course pi over 6. Let's write it 2 root 3 over 3, rationalizing this quantity and timesing it at the same time by pi over 6. And this will give me 2 over 18, which is a 9th. So I'll make this pi root 3 over 9. And I think, I don't quite remember. I remember it was a root 3 and a pi in the answer. I hope I'm not out by a factor of 2. I often write, I have made a silly mistake in there. I hope I haven't. Okay, I did put up there enrichment/discussion, because when I've done this particular integral, what I picked is, well, obviously the t transformation, or the little t identity substitution, if you prefer it, or Weierstrass, is kind of fairly standard these days. But as I explained earlier on, when we reach that stage here, let's put in a box. The Weierstrass substitution is an alternative. It is important, I believe it is important to know it. It has huge theoretical value and it's a viable alternative at times, but most of the time you don't actually need it. I didn't learn the Weierstrass substitution until very late when I was reading, when I was learning maths. I had a single textbook, then I invested money to get a second one because I was teaching myself, and that wasn't there, and it showed me a completely different way of doing this type of integrals, and it stuck with me since then. And later on in my life, obviously, as I learned more stuff and I looked at obviously other authors, other books, talked to other people, I learned obviously about the little t identities. This can be done actually in a very, very different way, but we'll get to the same result essentially. It's an alternative. Let's have a look what we can do in there. It's actually doing the little t's, but without doing little t's. So have a look at this manipulation. Okay, what can I do for something like that? This is what I can do. Leave the 2 where it is and break this into double angle. Treat this as being a double angle. 2 plus 2 sine theta over 2 cos theta over 2. 1 on the top, d theta. Simple enough step. What can I do next? I'm going to create the setup for this kind of integrals. When you're having on the denominator sine theta or cos theta, linear combination, possibly numbers. So for example, 4 plus sine theta, or 3 plus 5 cos theta on the denominator. Or you could have sines and thetas together. You can have sine theta plus cos theta, I don't know, minus 3, 1 over. When you're having linear combinations of these quantities, then this manipulation is all about creating a function of tan of theta over 2, and on the top a sec squared of theta over 2, because of course the tan of theta over 2 differentiates to the sec squared of theta over 2, and this is of course always my objective. So how I'm going to create this scenario? Well, I'm going to divide top and bottom of this fraction, of this integrand, by cos squared of theta over 2. I hope you can see what will happen in there. If I divide that by cos squared of theta over 2, the numerator of course will become sec squared of theta over 2. You can think of it also as multiplying top and bottom by this quantity. It's equivalent. So divide this by cos squared of theta over 2, or timesing by this. Of course, it will give us 2 sec squared of theta over 2. And if you divide this quantity here by cos squared of theta over 2, one of them will cancel this, and the other one will create this into a tan. So this is going to become, of course, plus 2 tan, not squared, of theta over 2. And that is that bit in there. Still d theta. No substitution used whatsoever. Okay. Remember what I was trying to do? I'm trying to create here a function of tan of theta over 2. I've got sec squared, no problem. Okay, we can go into tans. 0 and pi over 2. So the sec squared will become, of course, 1 plus tan squared is equal to sec squared. So it's going to be 2 plus 2 tan squared of theta over 2. I hope we are following. Standard straight mass identity. Plus 2 tan theta over 2, And of course, I've got the sec squared of theta over 2 on the top, the theta. And those who can see deep into this kind of problems, they can see that all I've done in there, I've done without doing the little t substitutions. I essentially have exactly what I had in the previous example, only is not substituted. So if you look there, I've got, of course, the 2, 2, 2. I don't have a 2 that I had on the previous one. I'm going to complete the square now on this denominator. So look what's going to happen. First of all, like before, 2, 2, 2. I like to have 4 and 4 here to complete the square instantly. Okay, so double top and bottom first of all. These are manipulations that are worth watching. Unless you've seen them live and someone's explaining to you the rationale behind all of this, they will not make sense. You cannot really put that into a still and show people. They will say, what on earth is going on in there? Plus 4 of this. And then we got, of course, plus 4. I'm going to write this plus 4 as 1 plus 3. And on the top, we got 2 sec squared of theta over 2. Those who might be a little bit lost, let's put the d theta here. All I've done is the following. A double top and bottom. 2 there, 2 there, 4, 4, 4. I wrote these 2 terms there as 4s. And this, which has become a 4, I borrowed 1 and I put the 3 on its own there. And now is just compacting this expression. 0 to pi over 2. This is a perfect square. 2 tan of theta over 2 plus 1 all squared. That's on the denominator. On the top we got a 2 sec squared of theta over 2. And the plus 3, because I tried to create an arctan, I'm going to write it like this. So complete the square. That's the whole point that I've done what I've done in there, to write it like this. There's my root 3. No major changes. And now, of course, somebody who is a mathematical heavyweight, or an integration heavyweight rather, can actually look at this and see instantly, but for the constants, that this is the arctan of this quantity over root 3. Because of course, this, if you differentiate the arctan of, just think of this bracket with the root 3 at the bottom, it will create, of course, this 1 over times the differential, of course, of 2 tan of theta over 2, which is something which looks like that. I'm going to reverse it, and hopefully I won't make any mistakes and shame myself, but if I do, please feel free to laugh. Things do go wrong at times, okay? So it's all part of the learning. All right, first of all, I'll differentiate an arctan of this quantity, 2. I'm going to get out of the way in a second so we can all see what I'm doing. Maybe I should have actually written it here. It's a little bit annoying now. Over root 3. So if I differentiate this quantity, this of course will produce this denominator. But in order to adjust it, I need to do the following things. First of all, I need the 1 over root 3. Part of the standard result. That's from this bit here. When I differentiate that, this argument, I'm going to get a 2. No, sorry, not a 2. This argument, I beg your pardon. I'm going to get a 2 from here. And I'm going to get a half from the differentiation of half theta. These 2 things will cancel. And then I'm going to create, of course, a sec squared of theta over 2. The sec squared of theta over 2 is there, but this 2 needs to be there from the beginning. And therefore, this 2 is already there. If you are lost with this particular one, please stick to the little t substitutions, or do another substitution on this one. I certainly think it's worth a little bit of practice and trying to follow what I'm doing. Okay, this integration at its best, I guess, is 5 stars. So yes, it is enrichment. Do not worry, this will never come up in an exam in this kind of form. And if we put our numbers in now and see what we're going to get, I forgot what answer we got actually for this one. Was it pi root 3 over 9? Was there a 2 there as well? I don't quite remember now. Okay, let's put the numbers in and let's see what we're going to get. We got a 2 over root 3. That is the 2 and the root 3 there. And we've got, of course, the arctan of what? Putting pi over 2 in there. Pi over 2 makes that pi over 4. Tan of pi over 4 is 1. 2 times 1 is 2, plus 1 is 3. 3 divided by root 3 is root 3. Is the arctan of root 3, which is a nice number. And then we're putting 0 in here. This will now die completely. So we got 1 over root 3. So we're getting the same numbers. I hope the number at the front is the same. The arctan of 1 over root 3. And this will simplify. Rationalizing this 2 over root 3, we're going to get 2 root 3 over 3. And this is going to give us a pi over 3 minus a pi over 6. And this is going to be a 2. Let's write it up here. Actually, it's not a good place. Let's write it up here because it's going to be part of our answer. And the answer that we're getting now is 2 root 3 over 3 times pi over 6. And this is 2 over 18. Pi root 3 over 9. I think there was nothing else in there. I hope I've done it correctly and we got the same answer both ways. My memory is terrible at the moment and I don't remember. I think that was the same answer. Okay, I hope you enjoyed it. I hope you followed it. There was a lot of things that just took place. Take some time to digest them. I'll see you very soon. And who's laughing now?